of the equations of the mathematics. The point is that I want to start this class with a story of a man who basically the man who chased the shadows. And the story that I'm telling you is 2,200 years back. So, who was this man? This man was a librarian, and his name was Eratosthenes. Eratosthenes, he was a librarian, and he was the man who could mathematically, without using mathematics, because it was not the time when people had telescopes and they could see the planet from outside, or they could have the satellites roaming around the planet. This man, who was a librarian, what he did was marvelous. It was miraculous because he could focus on the observation that he observed. Now, what the title is, The Man Who Chased the Shadows. Now, what was it that this man chased? And even the advent of the time was that when you had no telescopes, when you had no satellites roaming around the planet. And what he did, what he observed is, suppose we have a well, okay, and we have the rising of the sun. And what this man did actually is he observed a deep well when the sun was exactly on the top with respect to the ground. So if the sun is exactly on the top, you will directly see the bottom of the well, because even if you will put the rods around the well, you will not be able to see any of the shadows, because that tells you that the sun is exactly on the top. And if the sun is exactly on the top, then if you fix the rods around the well, you will not be able to see the shadow at the bottom of the well. And this observation was taken by this man. And what he observed, there used to have a place in Egypt, what was called Aswan. And in Aswan, somewhat around 21st of June, 2,200 years back, this man observes the well. And what he finds that at the bottom of the well, there is no shadow. But at the same time, having another well in Alexandria. So Alexandria is towards the north of the Egypt. And at the same time, the observation was made on another well. And in that well, they could observe a shadow. So this observation is taking place. There is a record of the observation over the same duration of the time. One well is telling you that there is no shadow, the sun is exactly on the top, and another well is telling you that there is a small shift. There is a shadow at the bottom of the well, and presuming that sun is very, very big and it's very, very far away from the planet Earth, we should not obtain the shadow in the both wells if Earth was flat. So this man is coming up with an argument. He's coming up with an argument, and the argument is that if you are able to measure a shadow in a well which is in the deep north of Egypt, and there's no shadow in a well which is in Aswan. It's the same place. Okay, so the existence of the shadow on another well is an indicative of the fact that Earth is not flat. And it's this observation on which this man worked. This man, a philosopher, a librarian of that time, he worked on this problem and he came up with an argument. Even it was the time when mathematics was not developed that much. But he could calculate the shift in the angle. He could measure the distance from Aswan to Alexandria. And by doing so, he could calculate the angle. And of that time, using the geometry, the geometry that was available in that period of time, he was able to calculate the circumference of the Earth. Could calculate the circumference of the Earth to a very, very greater accuracy. So what is it that led this man to come up with a very, very huge argument? This argument is not a simple argument. It was the time when everybody believed in flat Earth. And it's this curiosity that has led this man to know the reality, to understand the nature of reality. So what am I trying to tell you is science works if you come up with the right question. And if you come up with the right question, you will certainly come up with the right answer. And that will take this civilization on and on. So this is how I feel I can impress you by telling you the stories of the past who have really worked and who have really come up with the right questions to answer the right questions. When you try to find the answer to the right questions, you certainly come up with something which is a modification to the knowledge on the planet. Now, our journey is basically, now let's stop here. Our journey is basically to move on in the framework of time-dependent perturbation theory, and our target today is adiabatic approximation and certain approximation. Maybe the second one, I don't know whether we will be able to go to the certain approximation, but we will make an argument to complete that as well. So what we have is, we have the transition probability. And we have achieved it in our previous classes. And if I write down that transition probability as t, and this transition probability is, say, 1 by I h cross, then you have an integral 0 to t, and then you have a matrix element of m, you have a perturbation, say h dash and n, and you have an exponential function e to the power of I omega m n t dash dt dash. This whole thing we have to square. So this is giving us the transition probability. Now, before moving on, I would like to make a small modification in this equation. And how can I do that? And then we will proceed in the framework of adiabatic approximation. We will define that, and then we'll go to the next approximation, what is certain approximation. So what can I do here is, if you see closely, if I write t is the same thing, 1 by I h cross, and you have the integral 0 to t, and if I introduce 1 by iota omega mn, I can do that, and I have my own matrix element m h prime n, and for this I will write a time-dependent partial derivative, dou by dou t of I omega m n t dash, and then you have dt dash. And this whole thing is a square. And keep that thing in mind. Now you can see, if you take the time derivative of this exponential, it's e to the power of. If you take the time derivative of this exponential, what you will get I omega n outside. So the I omega n and n that I have introduced in the denominator, that will cancel. You will come back to your original equation. That you can understand. So this way, this iota will multiply with the iota. You will get iota squared. That will give you minus. But this is the mod of whole squared. That minus will go. And finally, what will be left inside is 1 by h cross omega mn. I think you can take the square of h cross, you can take the square of omega mn. So what will be your equation you will be left with? Your equation will be T is 1 by h cross square omega mn square. This is the thing that we have got out of it. Then what you have inside is the integral 0 to t, and you have the matrix element mh prime n, and then you have dou by dou t of e to the power of I omega mn t dash dt dash, and this whole square, you have the whole square of it. Okay, now this is my oversimplified transition probability of my system. Now, what I say, suppose the perturbation that you are introducing, because you are introducing the perturbation where you have a system of whose Hamiltonian can be completely calculated. And if Hamiltonian can be calculated, then what you do is you introduce the perturbation. Now what I do here is, if the perturbation that I introduce to the already known Hamiltonian, if the perturbation takes a longer time, if it takes the longer time, so what does that mean? So if I have an infinite well potential like this, and you know the potential, you know the Hamiltonian of the system, and what you do is you introduce a perturbation. But that perturbation takes a longer time. That means it goes on and off slowly. So going on and off slowly means, say for example, it started from 0 and it reached here by say 10 milliseconds, for the sake of argument. Now this kind of perturbation that you have introduced in the potential well is adiabatic. Then if this is adiabatic, then what is sudden? So for sudden, we have the same potential, we have the perturbation that we are introducing, but that perturbation lasts for say 10 nanoseconds. Now, these seem to have the same kind of perturbations, but there's a difference of time. In the first case, the time is taking longer. So this kind of perturbation is adiabatic perturbation. It is adiabatic time-dependent perturbation that you are introducing in your system. And this kind of perturbation, here you can see a shot. The same thing is happening, but it's happening in a very, very short period of time with respect to the milliseconds. Here you have nanoseconds. So this kind of perturbation is called sudden. Here we make use of sudden approximation, because things are happening suddenly. And in this case, the perturbation you are introducing to the system, it's going on slowly. So this kind of perturbation is called adiabatic perturbation. Adiabatic, here we use a mathematical approximation, what's called as adiabatic approximation. So this is my adiabatic approximation. We deal out the problems using adiabatic approximation, where the perturbation that you are introducing in your system is slow. And here, where the perturbation that you are introducing into your system is fast with respect to this, then this kind, here we make use of sudden approximation. This expression is already evaluated, and let's proceed from here to reach out to a simplified equation And then from the result that we will obtain from solving this and modifying this equation, uh, there we would like to discuss the two important approximations. One is adiabatic approximation and another one is certain approximation. I have already given you the explanation what adiabatic means and what certain approximation means. So the perturbation that you are introducing in your system, if it goes for the longer time, if it evolves over a long period of time, then the perturbation that you are introducing in your system is adiabatic in nature, and you make use of adiabatic approximation. And at the same time, if the time of the perturbation that is introduced in the originally known system, this kind of approximation is what's called as certain approximation. So let's formulate this equation a little bit. So what we can do is we can think of writing this t as 1 by I h cross integral 0 to t, and you will have matrix element h prime, and here I will introduce the time derivative dou by dou t, and this is e to the power of I omega mn t dash dt dash. But since if you take the time derivative of this exponential function, you will have something in the numerator. What will be that? Will be the internal derivative of this exponent. So here if I write I omega mn, so what's going to happen here is once you take the time derivative, I at omega mn will come out and they will cancel. So your equation is not going to change. You will retain the originality of your equation. So this is whole square. So what we can do here is we can multiply this iota square. It will give us -1. Since you have whole square, so it will automatically become plus. So what will be outside will be 1 by h cross square omega mn square. Then inside you'll be left with the integral 0 to t, and you have the matrix element m h prime n e to the power of, no, it has to be the time derivative of dou by dou t of e to the power of I omega mn t dash dt dash whole square. Now, proceeding from here, what we would like to do is to integrate this these things which are within our integral limiting from 0 to t, and then obviously we are supposed to take the square of that. So what we'll be left with is we will have the transition probability. It will be 1 by h cross square omega mn square. Okay, you can think of using the UV rule here, and if you use the UV rule, what will happen, treating the first matrix element as u, so it will be m, h prime, and n, and integrating the exponential part will give you e to the power of I omega n t dash. Because the other part is the time derivative of the exponential. Once you integrate it, this differential and integral will cancel, so you'll be left with e to the power of I omega mn t dash. Then you will have minus integral 0 to t, and the differential of u, that's dou by dou t of m h prime n, and the integral of this part, again, this differential and integral will cancel, so you'll be left with the exponential function. So you will have e to the power of I omega mn t dash, and you will be left with dt dash. Now at the same time, this is the whole square. We have to keep in mind it's all square because we are calculating the transition probability. We're boiling down this equation to some reference equation where we can discuss the result in terms of the adiabatic approximation, and then we can take this discussion to the certain approximation. So what's going to happen here is, looking onto the boundary conditions of our problem, at t equal to 0, the perturbation, which is h prime, and in our case, assuming it to be v naught, this v naught will be 0, and at t equal to t, again this perturbation, that is h prime, v naught, this will vanish. So what's going to happen in the first part of this bracketed term? This bracketed term will automatically lead to 0 when you apply the limits to this result from 0 to t. So this part of the bracket will cancel. So your transition probability will come up as, so t will come up as 1 by h cross square omega mn square, and then you will have the square of that integral, so the minus will automatically go. So this will be integral 0 to t dou by dou t of the matrix element m, h prime, and n, and then, and then you will have the exponential part e to the power of I omega mn t dash dt dash. But this is all square of it. So this is all square of it, and this is my basic equation, and I would like to use this equation to discuss the two important cases. The first case is adiabatic approximation. Adiabatic approximation. So in adiabatic approximation, the assumption is what? The assumption is that the perturbation that you have introduced, it's going to vary slowly in time. So if the perturbation that you have introduced in your system is varying slowly, then this term, the time derivative of this matrix element will be treated as a constant. So it will come out of the integral. So in that case, t will be 1 by h cross square omega mn square and dou by dou t of the matrix element m, h, and n. H prime is the perturbation, and then you'll be left with 0 to t e to the power of I omega mn t dash dt dash. Now what is important is that this is whole within the brackets, and you have to take the square of it. Now if you take the square of it here, you will keep the square for this whole thing, and you would like to keep the square for this whole thing. And you can see from our previous classes, we have already integrated this kind of function, the exponential function, that's carrying the same symbols as the symbols that you can see here. And the result of this integral is, it is sine square omega n mn by t. So what will be t here? So t, the transition probability, is going to be 1 by h cross square omega mn square, and then you will have dou by dou t of the matrix element of m, h prime, and n, and this whole square. And the result of that integral will give us sine square omega mn t by 2. Now what does this equation tell us? This equation tells us, suppose you have two energy states, say this is E1 and E2, assuming that E2 is greater than E1. Now how we can translate this equation into an adiabatic approximation? One is that this term that you have, what is this? This is 1 by h cross square omega mn square and dou by dou t of n h prime and the square of this whole value is very, very less than the difference in the energy, say E2 minus E1. Or let me call it E1 minus E2, because the transition has to take place from E1 minus E2. Now, since the term that's here is very, very small than E1 minus E2, then you can simply say that this term is tending to 0. And the transition between E1 minus E2, it's also tending to 0. So what does it mean? It means when your system is evolved adiabatically, then the probability of the particle, say for example an electron in the lower energy state, the probability for this electron to move from the ground energy state to the first excited state is equal to 0. There is no transition probability. You will not make any transition. Your system will maintain its originality even though you are introducing the perturbation to your system. Now the next case is the certain one. So in case of certain approximation, so what's our basic equation is T is 1 by h cross square omega m n square, and you have a bracketed term. Then you have an integral from 0 to t, and you have the time derivative of the matrix element, and you have the exponential function e to the power of I omega m n t dash dt dash. This is all bracketed to a square. Now, in case of certain approximation, as I explained to you in the beginning of this class, that for certain approximation, the perturbation that you are introducing in your system, it takes a very, very short time to evolve with your system. So if it takes a very, very small time to evolve with your system, in that case, this exponential that you have, this exponential will act as a constant. So for certain approximation, the exponential part of this equation will come out of the integral. So what will come t as? So t can be written as 1 by h cross square omega mn square, and then you will have e to the power of I omega mn t dash by nothing raised square, and what will be left inside in the integral is 0 to t dou by dou t of m h prime, which is the perturbation that you are introducing, and this perturbation is there for a very short span of time. This will be whole square. Now you have an exponential function. You have to calculate its magnitude. So when you calculate its magnitude, it's a complex function times its complex conjugate. It will lead us to the number 1, because when you multiply the two, you will get the power raised power 0, and anything raised power 0 will take us to 1. So transition probability will come out to be 1 by h cross square omega mn square, and then you have your own 0 to t. I think you can also cancel this integral with the derivative. So when you do that, what you'll be left with is m h prime n whole square. Now what does this equation tell us? This equation tells us that you have a probability of transition, that your particle, your electron, will make a transition from the ground state to the first excited state, say in the case of an atom. So your system will accurately make a transition. There's a very good probability of making a transition, and that transition has to be allowed transition. The transition will take place from one energy state to another energy state, because our transition probability is simply depending on the square of the matrix element. So what is the conclusion of the two results that we have obtained? The first one was adiabatic approximation, in adiabatic approximation, we assumed that the time evolution is very slow. The system is adiabatically evolving. The perturbation that you are introducing in your system is adiabatically evolving. In that case, we saw that the transition probability is zero. There will not at all any kind of transition take place from one state to another state. But if at the same time, if we decrease the evolution of time, if we decrease it marginally to a very, very small shot, then there is a measurable probability that the electron may make a transition from one energy state to another energy state. So with this, I hope you find this useful. I hope you find this helpful to proceed on to solve the problems based on these approximations.